Hello everyone, this is Flaw Academy. Because AP test is coming, I wanna make several videos to have a quick review about some important knowledge points in AP calculus and teach some skills to solve the questions. I will not actually review all of the knowledge points, but I will cover all of the difficult and important parts in the AP calculus test. For each part, I will make two kinds of videos, and one is about the knowledge points, and another one is about some examples and practice. Moreover, I will talk about some proof. If you guys do not want to listen to this part, I recommend you guys to pause this part and take notes about the conclusion of the proof. And according to the data recorded by a man whose identity is unknown, I will first talk about series, which is our topic in this video. Okay, let's begin now. In series, I think the most important thing is to determine whether or not a series is convergent. So first, I will talk about this part. There are three main tests: the comparison test, the integral test, and the ratio test. By the way, I think the most useful test is ratio test because you can use it to solve almost all of the questions about determining convergence. For comparison test, we suppose that there are two series, the series AN and the series BN. And AN and BN are larger than 0 for Ln. And we can get two conclusions here. The first one is that if the series BN is divergent and AN are larger or equals to BN for Ln, we can get that the series AN is also divergent. And the second conclusion is that if the series BN is convergent and AN are smaller or equals to BN for Ln, so we can conclude that the series AN is convergent. Now we will prove this test because we know that the series BN is divergent. So we can say that the series BN equals to infinity. And also we know that N is larger or equal to Bn for Ln. So we can get that the series An is larger or equal to the series Bn. And we know that the series Bn equals to infinity, so that we can conclude that the series An is larger or equal to infinity. So we can get that the series An is divergent. And then about the second conclusion, because we know that the series Bn is convergent, so that we can see that the series Bn equals to I. The I is a real number. And we also know that ANs are smaller or equal to BN for Ln. So we can conclude that the series AN is smaller or equal to the series BN. And because the series BN equals to I, so that we can conclude that the series AN is smaller or equals to I. Thus, we can conclude that the series AN is convergent. And then I will talk about integral test. We suppose that fx is a decreasing positive continuous function from 1 to infinity, and fn equals to an for Ln actually. And we can get two conclusions. And the first one is that the integral fx dx from 1 to infinity, if this one is divergent, we can conclude that the series an is divergent. And the second conclusion is that if the integral fx dx from 1 to infinity is convergent, we can find that the series an is also convergent. And then I will talk about the proof of integral test. And first we draw a graph of fx. And this is 1, this is 0, and this is 2, this is 3, this is 4, and this is infinity. We can find that the rectangular area is A1, and this rectangular is A2, and this one is A3, and this one is A infinity. So we can find that the area of those rectangulars are actually the series an. And this one is larger than the integral fx dx from 1 to infinity, according to the graph. Because this is divergent, we can conclude that this is divergent too because of the comparison test. In order to prove this, we draw another graph of fx. This is 1, this is 0, this is 2, this is 3, this is 4, and this is infinity. And the area of this rectangular is A2, and this is A3, and this is A4, and this is A infinity. So the area of those rectangulars is represented by this. And this is smaller than the integral fx dx from 1 to infinity. And because this is convergent, we can conclude that this is also convergent. And because the series an equals to this plus A1, so we can see that the series an is also convergent. Then the last one and the most important one, the ratio test. For ratio test, we suppose there is a series an, and the limit of the absolute value of an plus 1 over an as n approaches infinity equals to r. So we can conclude that if r is larger than 1, the series is divergent. And if r equals to 1, the method is inconclusive. and if the R is smaller than 1, the series is convergent. And in this test, the proof is a little bit complicated and time-consuming, so that I will not talk about it. And now we have a summary about this video. And in this video, we mainly talk about 3 tests. The first one, the comparison test. For comparison test, we suppose there are 2 series, the series AN and the series BN. And we got 2 conclusions here. And the first one is that if AN is larger or equals to BN for Ln, and the series BN is divergent, we can know that the series AN is also divergent. And the second conclusion is that if AN is smaller or equals to BN for Ln, and the series BN is convergent, we can know that the series AN is also convergent. And the second one, the integral test. For integral test, we suppose there is a fx, which is a decreasing positive and continuous function from 1 to infinity, and Fn equals to An for Ln. Then we can conclude that if the integral fx dx from 1 to infinity is convergent, we can know that the series An is also convergent. If this is divergent, we can know that the series An is also divergent. And the last one, the ratio test. In ratio test, we suppose there is a series An, and we determine the limit of the absolute value of An plus 1 over An as n approaches infinity. And if the value R is larger than 1, the series An is divergent. And if the value is equals to 1, then this test is inconclusive. And if the value is smaller than 1, the series An is convergent. If you are interested in our video, please leave a like and subscribe our channel.